Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So you can recall that in the last lecture we started a discussion on balance in complete block design. We had learned that how the treatments are going to be assigned in different blocks under the setup of BIBD, and we had also understood that this is not an orthogonal design, and this is also obviously an incomplete block design. So now we have to think about the further properties. Then we had found or we had stated three different properties, and then we also had the proof of those properties. The proofs of those three properties can be obtained based on the mathematics or algebra that we did in the last lecture, but these three properties also have some interpretations, and the validity or the sort of proof of these three properties can also be given on the basis of some arguments, that what is BK, what is VR, and so on. So now in this lecture we will continue from the last lecture, and first we will try to have the proofs of the three properties on the basis of some arguments. And then we will try to have some basic definitions which are related to the BIBD, and then we will start attempting the intra-block analysis of variance. So let us begin our lecture. So first we try to see here that what are the three properties which were considered in the last lecture. So you can recall that the balance in complete block design is going to be indicated by the 5 parameters BK, VR, and lambda, and these parameters are not chosen arbitrarily, but they have to satisfy these three conditions: BK is equal to VR, lambda into V minus 1 is equal to R times A minus 1, and B is greater than or equal to V. So now we had seen in the last lecture that how we can obtain these three properties on the basis of the mathematical arguments. Now we will have a sort of interpretation of these three conditions. So I will try to consider here these two conditions, first and second, and then after that third we will not be able to do it because it is quite complicated. Right. So so first let us try to attempt with the property of BK is equal to VR. So this condition is related to the total number of plots in an experiment. How? Now if you try to see in this BIBD, you have considered B blocks, and each of the block has K plots. Right. So now if I ask you a very simple question, what is the total number of plots? So there are B blocks and each block has K plots, so this number is going to be BK. Right. So the total number of plots in the setup of BIBD that we are considering is BK. Now in case if you recall, we have here V treatments, and each of the V treatment is being replicated R number of times, and there was a condition that each of the treatment can either occur in the block not more than once, or it may not occur at all. So these V treatments are given to the blocks in such a way such that each treatment is replicated R times, such that each treatment occurs at most once in block. So if I ask you what is this number, or if I ask you in a much simpler way, where are you going to give these treatments? These V treatment, each treatment being replicated r times such that it occurs at most say 0 times or 1 times. So, where are you going to give these treatments? Obviously, the answer is to the plots. So, all these plots which you have computed here, the total number of plots to be here b into k, these number of plots are going to contain these V treatments such that each of the treatment is repeated r times and each treatment occurs either 0 time or 1 time inside the block. So, that means can you say here that the total number of plots containing all the treatment is VR? And now this both the statements, that is the total number of plots and the total number of plots containing all the treatments, they are the same, because both the statement count the total number of plots in different ways or in 2 different ways. Hence, we can say here Bk is equal to Vr. So, that is the proof of this property. Now, we come to the second property, which was r into a minus 1 is equal to lambda times v minus 1. So, now you know from the setup of BIBD that each of the block has k number of plots. So, the total pairs of plots in a block will be k choose 2, mean that total number of ways in which you can choose 2 plots out of k plots. So, that is k choose 2, which is equal to here k into a minus 1 by 2. And now, if you try to see here how many blocks are there, there are B blocks. So, the total pairs of plots such that each pair consists of plots within a block will become here B into k choose 2, which is B into k minus 1 upon 2, right. So, this is first statement. Now, we try to understand that since there are V treatments, so the total number of ways in which you can choose 2 treatments out of V treatment is going to be V choose 2. So, the total number of pairs of treatments will be V choose 2, which is equal to here V into V minus 1 by 2. And now, if you try to recall the conditions of the BIBD, that every pair of treatment is being replicated lambda number of times in the design. So, now since each pair of treatment is replicated lambda times, that is each pair of the treatment occurs in lambda out of E blocks, then we can say here that the total number of pairs of plots within blocks should only be lambda into V minus 1 into V divided by 2, that is lambda into V choose 2. So, now if you try to see this statement, this is say call it as a statement number 2. This statement number 1 which you have obtained here and this statement number 2 which you have obtained here, they are the same. So, now we can write down here B into k choose 2 is equal to lambda into V choose 2, that is B into k minus 1 upon 2 is equal to lambda into V minus 1 upon 2. Now, we try to solve this condition. So, this 2 and 2 gets cancelled out and you already have proved that Bk is equal to Vr, right. So, you can write down here instead of this here Bk, we can write down here Vr into k minus 1 is equal to lambda into V minus 1. This V gets cancelled out and we get here R into k minus 1 is equal to lambda into V minus 1, right. So, now we have the proof of the property number 2 and you can see here that is very simple proof. Now, similarly, you can also have the proof of property number 3 that B is greater than or equal to V, and this proof was given by Professor R.A. Fisher, but it is quite long. So, we are not doing here. Now, you have understood that what do we really mean by the proofs of the same properties from different point of view. Right, okay. So, now I come to first on some basic definition terminologies which is used in the case of BIBD. Now, when you are trying to write down here the name BIBD, you understand what is the meaning of IBD, that is incomplete block design. That means all the treatments are not occurring in all the blocks. What is the meaning of B? That is balanced. That we have not yet talked about it. So, now in this BIBD, the meaning of this balance is as follows. Actually, there are two types of definitions which are trying to define the concept of balancing. One here is variance balanced and another is efficiency balanced. At this moment, we are going to discuss about the variance balancing, and we will talk about the efficiency balancing later on, because actually when we will try to conduct the analysis of variance at that time, we will get there a factor that is called as efficiency factor. So, then I will be giving you the definition of balancing from the point of view of efficiency factor. So, at this moment it is difficult because you have not yet seen how this efficiency factor will come. So, that is why I will try to do it later, but at this moment let us try to first understand the definition of balanced design, which is actually here the variance balanced. But at this moment, at this stage, I would like to make here a clarification that in common language in the designs of experiment, that whenever we are talking of the balanced design, most of the people will take this definition of variance balance to be as default. Right. So, unless and until it is specified that we are talking about the balancing in terms of efficiency factor or efficiency balance, usually the meaning of balance is considered as variance balanced. Right. Okay. So, what is this definition? A connected design is said to be balanced, or the variance balance more precisely, if all the elementary contrasts of the treatment effects can be estimated with the same precision. Now, in case if you try to understand this definition has the following contents. One here is this one, connected design. Second here is elementary contrast, and third here is same precision. Now, you have to recall these three definitions and then you have to club it together. So, do you remember that we had earlier discussed the concept of connected design, where we said the design is said to be connected if all the elementary contrast of that design are going to be estimable. So, that means we are going to consider here the treatments in the form of elementary contrast, and they are going to be estimable. Now, when you try to find out the variance of the estimates of this treatment effects, then if all pairs of estimates of treatment they have got the same variance, that means they have got the same precision, then the design is said to be balanced. So, in very simple words, consider a design in which there are certain number of treatments try to estimate those treatments, try to construct their elementary contrast, try to find out their variances, and if every pair of treatment in the form of an elementary contrast has got the same variance, then we call that the design is variance balanced. So, obviously, this definition does not hold for those designs which are not connected, they are disconnected designs. So, in that case this definition will not hold true, because in that case all the elementary contrasts are not going to be estimable, that is the basic definition. So, now you can see this is what I was requesting you in the last lecture, that when you come here, try to come here with the good revision of the previous definitions, because now I have used here these definitions here directly. Right. Now, after this I try to give you here some more definition. So, the next definition is what is a proper designs, right. So, any incomplete block design where you are trying to take here K1 equal to Kb equal to say as K, this is called as proper design. What is the meaning of this? Do you remember that when you consider the incomplete block design, then you had considered different number of plots in the blocks, and you had denoted by this Ki to be the number of plots in the ith block. So, now you are trying to say that each of this Ki is going to be the same as K, or in very simple words, all the blocks are of the same size and the size of the block here is small k. Once again I will have your attention that in the case of incomplete block design, you had considered K as a vector quantity K1, K2, Kb transpose. But now here in this case in IBD, but in this case here K here is a scalar quantity. So, you have to be very careful when you are trying to do this algebra. So, now you can see here in the case of BIBD what you have considered. You have considered that every block has got the same number of plots K. So, that is why the BIBD what we are considering here, that is a proper design. Now, what is here a symmetric BIBD? So, BIBD is called symmetrical if number of blocks is the same as the number of treatment, that is B is equal to V, right. So, in this case what will happen, because B is equal to V. So, we had this relationship BK is equal to VR. So, we are trying to cancel here B and V, and in this case we will get here K equal to R, right. So, now this K and R are going to be the same, that the number of pairs of treatments common between any two blocks is going to be lambda, right, and lambda is the number of times a pair of treatment occurs in the entire design, that is among all the blocks. Now, after this we have a definition of resolvable design. So, a block design of B blocks in which each of the V treatment is replicated R time is said to be resolvable if B blocks can be divided into R sets such that the size of every block will become B upon R. So, B upon R blocks each such that every treatment appears in each set precisely once, right. So, obviously, when you are trying to say that the block size is for all practical purposes is going to be like B upon R, or the size of each set is going to be B upon R, then B upon R cannot be any number, it has to be some integer, and the condition that B is a multiple of R. So, obviously, in the case of such a design which is a resolvable design, B is a number such that B is a multiple of R. Now, there is a result that in such a case what happens? So, if you try to consider here a BIBD, which is a design with parameter V, B, R, K and lambda, and suppose if B is divisible by R, that means the design is resolvable, then B is going to be greater than or equal to V plus R minus 1. Right. So, now let us try to prove this theorem. So, suppose that B is equal to NR, where N is some here positive integer greater than equal to greater than 1. Right. Now, you have a property of BIBD here as lambda into V minus 1 is equal to R into A minus 1. So, from here we can write here directly here that R is equal to lambda V minus 1 divided by K minus 1. And now, if you try to see here, you have the condition here VR is equal to BK or BK equal to VR, what you have just done. So, now you are assuming here that B is expressible as NR. So, you can replace here this B and we can write down here NRK is equal to here VR. Right, then R will get cancelled out and we get here V is equal to N times K. So, what we try to do here, that we try to replace this V by here N K, and then I try to adjust this term which I can express as here lambda times N minus 1 upon K minus 1 plus lambda N. So, now if you try to analyze this expression, can we see what we observe here? Because you can see here that N is going to be greater than 1, this K is also going to be greater than 1, and lambda and N both are integer. So, lambda into N is also going to be greater than 1, right, and that is an integer. So, now since R has to be an integer here, so I can say here that this term here lambda into N minus 1 upon K minus 1 is also a positive integer. So, if I try to say the same thing, you can see here in this term, this R is going to be an integer, lambda into N, this has to be an integer because lambda and they are the number of times. So, obviously, when you are trying to express this R as an integer as the sum of two numbers and out of which one number is an integer. So, obviously, this second part which is lambda into N minus 1 upon K minus 1, it has to be an integer. But now, how to say that what we are saying is right or wrong? So, we try to just assume its opposite, and if possible we assume that B is less than V plus R minus 1. So, now you have since assumed here that B is equal to here NR. So, I write down here B here as a NR, and so this becomes here NR is less than V plus R minus 1, and if you try to simplify here R is on this side, this will become here R into N minus 1 is less than V minus 1. Now, if you try to see here this property using the property number 2, that lambda times V minus 1 is equal to R times K minus 1, we can write down here this V minus 1 here as say R K minus 1 upon lambda. So, now if you try to see here, this R and R gets here cancelled out, and this lambda comes over here, this term comes over here. So, this becomes a lambda into N minus 1 divided by K minus 1 is less than 1. Now, if you try to see, is it really possible? You are trying to assume that this quantity, this is an integer, and integer is less than 1. This is a contradiction, because the integer cannot be less than 1. So, that means the assumption what you have taken here, that b is less than v plus r minus 1 is not possible. When this is not possible, then what is possible? Just the opposite of this, and the opposite of this is that b is greater than or equal to v plus r minus 1. This condition holds correct. So, and if you try to see, this is what you wanted to prove, that b is greater than or equal to v plus r minus 1. So, now we have proved this result also. Okay, so now we have completed all the basic definitions and fundamentals that are required in this chapter. I am not saying that I have covered all the fundamentals and definitions which are related to the balanced incomplete block design, but I have given you here sufficient which are required for our course. Now, we come to the aspect of analysis of variance. So, now in case if you try to recall that when we did the incomplete block design, we had considered a two-way model which has block effects as treatment and treatment effects, and there were certain conditions for the incomplete block design, and then we had obtained the estimates of beta and tau using the least square principle. And when we were trying to obtain the normal equations, then we had seen that the normal equation can be obtained in two possible formats, because all the parameters beta 1, beta 2, beta b and tau 1, tau 2, tau v, they were not estimable. So, we had two options, that we try to eliminate the block effects and we try to estimate the treatment effects, or the second option was that we try to eliminate the treatment effects and that we try to obtain the block effects. So, based on that, we had finally concluded that when we are trying to deal with the incomplete block design, then it matters what we want to do, whether we want to test the hypothesis related to the equality of block effects, that is H naught beta 1 equal to beta 2 equal to beta b, or are we interested in the null hypothesis related to the equality of treatment effects, that is H naught tau 1 equal to tau 2 equal to tau v. And based on that, we have to opt what we want to do. In case if we are interested in the hypothesis about the equality of the treatments, then from the normal equations we have to eliminate the block effect and we have to estimate the treatment effect, and based on that treatment effect we have to find the adjusted treatment sum of squares, and the block sum of square is going to be unadjusted, and then from there we have to find out the SAC, the TSS remains the same, and then we can conduct the analysis of variance. On the other hand, in case if you are interested in the null hypothesis H naught beta 1 equal to beta 2 equal to beta b, that is the equality of the block effects, then from those normal equations you have to eliminate the treatment effects and you have to obtain the reduced normal equations in terms of block effects. From there you are going to estimate the block effects. Then using those block effects you have to find out the adjusted sum of square due to blocks, and in this case the treatment sum of square is going to be found as unadjusted. So, in this case you will find the adjusted block sum of square and unadjusted treatment sum of squares, and from there you will try to obtain the SSE, and then TSS remains the same, and then you will try to find out a statistics to conduct the analysis of variance. And this was just opposite to the case what we did in the case of RBD, that you can obtain the sum of square due to treatment of block in the same way. So, now the question is this, in this case BIBD, what we want to do? Would you like to consider the null hypothesis related to the equality of treatment effects or to the block effects? Well, you can do both, means from the conceptual point of view, both of them are possible. But if you try to think from the application point of view, whenever we are trying to conduct a design of experiment, then the experiment is the experimenter who is trying to conduct the experiment to achieve some result. That experimenter is more interested in getting an outcome related to the treatment effects. The experimenter may not be interested in the block effects. This means, suppose if somebody wants to conduct an experiment to know what is the effect of different doses of the medicines, that experimenter will come to us because we are doing statistics, and the question which is going to be asked is simply, can you please let me know whether the effects of different doses of the medicine, they are the same or they are the different. The experimenter is not interested whether we are trying to conduct this experiment with blocks or without blocks, blocks of equal size, blocks of unequal size, no. Usually they are not interested. But this is our choice, that is the decision which is taken by a statistician, that whether the blocks have to be constructed or not, and if yes, then how the blocks are going to be constructed. They have to be within homogeneous, between heterogeneous, or vice versa. So, now keeping this fact in mind, that now we are going to develop the analysis of variance, which is going to be used in most of the applications in real life, we will consider here the test of hypothesis for the equality of the treatment effects. But this does not mean at all, you must not get confused that because the test of hypothesis for the block effect is difficult or XYZ, any reason we are not doing it. No, we can do here both. We all are capable of doing both. We have very clear cut results available, but because of that reason only we are going to consider here only the test of hypothesis about the equality of treatment effects. So, with this point of view, we now first try to understand how to conduct the analysis of variance in case of intra-block analysis, right. So, we are going to consider here the reduced normal equation of the type q is equal to c tau. Do you remember that when we obtained the reduced normal equation for the block effects, they were like p is equal to d beta? So, we are going to consider here the reduced normal equation of the form q is equal to c tau. Now, do you think that I should give you here the complete derivation that how are we going to obtain the reduced normal equation of the form q equal to c tau? We already have done it. So, now I would not like to use my time in repeating the same thing here again. But what I am going to do here, that I will try to borrow the expressions of q, c tau, or say q I, c j j, c j j prime, etc., that we have done in the case of incomplete block design, and then I will try to find out the values of those expressions in the setup of BIBD. So, this way we will understand it and we can save our time also. So, let us continue with the lecture. So, now we are going to consider here the intra-block analysis of So, we are going to consider here the same model that we considered in the case of incomplete block design, that is y I j is equal to mu plus beta I plus tau j plus epsilon I j, where I is going from 1 to b and j is going from 1 to v, where your mu here is the general mean effect, beta I here is the fixed additive ith block effect, and tau j here is the fixed additive jth treatment effect. Right. And remember one thing, that in the case of intra-block analysis, we consider the fixed effect model. It was only during the inter-block analysis we had considered the mixed effect model, where we took the block effect to be random. And here epsilon I j, this is the IID random error, and we assume that here with epsilon I j here as a following a normal distribution with mean 0 and variance sigma square. Right. As I said, now we do not need to develop the analysis of variance for BIBD right from the beginning, because BIBD is an incomplete block design, and the analysis of incomplete block design and its analysis of variance that has already been presented in the earlier module, means earlier chapter. So, we implement those expressions that we had already found directly under the setup of this BIBD, and we are trying to use the conditions that are imposed for BIBD, like as bk equal to VR lambda equal into V minus 1 is equal to RK minus 1 and B greater than or equal to V. Right. So, now we will use here the same symbols and notation that we had used earlier. So, we can present here the block totals by BI, which is here summation over j y I j, the treatment totals by the same symbol Vj, which is here summation over I goes from 1 to b y I j, the adjusted treatment totals were for Qj, and j is going from here 1 to v. So, we had Q1, Q2, Qv, and the grand total, that is the sum of all the observation, which is double summation over Yij by G. So, that is the same symbols and notation, and I will try my best to use the same symbols and notation that we had used earlier, so that there is no confusion. Now, as I discussed, that we have here two options, that whether we want to consider here the null hypothesis about the equality of treatment effects or the block effects. So, we are going to consider here the null hypothesis about the equality of treatment effects. So, for that we had obtained the reduced normal equation, in which we had removed or eliminated the block effects from the normal equation, and then the normal equations were solved to obtain the treatment effects tau j hat, or in the form of vector it was tau hat. And after that we had found those intra-block equation of the treatment effects, that was actually the reduced normal equation in the matrix notation as Q is equal to C tau hat. And from there you can obtain here the estimate of tau hat. And do you remember that we had also discussed that rank of C is not equal to V, right. So, you have to just remember that rank of C equal to V. So, when we are trying to find out here tau hat, we have to find out here the generalized inverse of C, right. So, tau hat is going to be generalized inverse of C into Q. So, now the situation has come where we are assuming that we are at a stage. Suppose we started from the beginning, and now we have done all the algebra, we have obtained all the normal equations, and then finally we have reached to a condition where we have Q equal to C tau. Now, the next question comes, what are the forms of the matrix C and vector Q in the case of BIBD? Once I can find it out, then I can obtain the Q and C in the case of BIBD. So, let us try to find out first the structure of here matrix C. So, C is a V by V matrix. So, this matrix will have two types of elements, diagonal elements and off diagonal elements. So, the diagonal elements of C, if you remember the incomplete block analysis where we obtain the Cjj and Cjj prime in the initial part of the incomplete block design chapter, we had obtained that Cjj was obtained there as say R minus summation I goes from 1 to P B n square I j upon k. Right. Now, if you try to see what is here the value of this quantity here, summation I goes from 1 to B n square I j. Now, if you try to see in the case of BIBD, this n I j is going to take only value here 0 and 1. So, this summation is going to be some like 0 square plus 1 square plus up to here some whatsoever be the construction of the design or the way in which the treatments are given to the blocks. So, now here only this ones are going to appear in this complete sum. So, now the question is this, how many ones are going to be there? You are assuming that by Nij equal to 1, we are going to indicate that the treatment is present in the block, and with 0 the treatment is absent in the block. So, how many times you are trying to repeat a particular treatment in the entire design? That is R time. So, the summation is going to be here R. So, this Cjj becomes here R minus R upon k. And now, what will happen to the off diagonal elements of the matrix C? So, if you remember, we had earlier obtained the expression for Cjj prime where j is not equal to j prime, that is indicating the off diagonal element, which was minus 1 over k summation I goes from 1 to b Nij into Nij prime. Now, as we had discussed that these values Nij and Nij prime, in the case of BIBD, they are going to take here the values 0 and 1. So, there are 4 possible combinations, that Nij and Nij prime both take value 0. So, their product, that is Nij and Ij prime, that is going to be 0. If Nij equal to 0 and Nij prime equal to 1, then this product is going to be 0, or Nij equal to 1 and Nij prime is equal to 0, that means the jth treatment means occur in the ith block and the j prime treatment does not occur in the ith block. Then in that case, this product is going to be here 0, and the last option is this, both Nij and Nij prime they are equal to 1. So, their product is going to be here 1. So, now you can see here that this summation, this is going to be like here minus 1 over k, and summation will be like 0 1 plus 0 plus something. So, there are going to be some number of 0 and some numbers of 1. Now, the question is how many 1s are going to be there. So, when I am trying to take here the product, say Nij into Nij prime, that is indicating that both j and j prime treatment they are occurring in the same block I. So, that means we have assumed according to the definition of BIBD that there are lambda times a pair of treatment appears in the entire design. So, this summation is going to be here lambda, and so we can write down Cjj prime as minus lambda upon k. So, these are my here off diagonal elements of the C matrix. Now, what about the adjusted treatment totals? So, if you try to recall, we had earlier obtained the expression of Qj here as say Vj minus 1 over k summation I goes from 1 to b and Ij Bi. So, now if you try to see here what is happening, if you try to look at this expression, say Nij Bi. Now, Nij is going to take here 2 possible values 1 and 0. So, now if you try to find out this expression, say Nij into Bi, so this is going to be something like 0 times B1 plus 1 times B2 plus here like this. So, wherever Nij equal to 0 is there, the entire contribution of this product will become 0, and wherever Nij is equal to 1, the entire contribution of this product will appear as the block total. So, Bi will appear in the summation only when Nij is equal to 1. That means you are going to consider the sum of only those block totals in which the J treatment is appearing. So, this statement I try to indicate by this new symbol, where I am taking here this summation over Bi, but in order to indicate that this summation is not over all the blocks I goes from 1 to B, I introduce here a symbol I, and inside the bracket parenthesis I will write here J. So, this symbol is going to indicate that the sum is being taken over those blocks which are containing the Jth treatment, right, and sum of all such block totals, that is being indicated by here a new symbol here Tj. So, Tj is going to indicate the sum of all the blocks where the J treatment is occurring. For example, if I say here, suppose I have here couple of blocks, say block 1, block 2, block 3 and here block 4. Suppose if I say treatment number 1, tau 1 is appearing in block number say 2 and block number 4, and it is not appearing in block number 1 and 3. So, that means I am going to write down here T1 is equal to B2 plus B4, right. And similarly, if treatment number 2 that is appearing in say block number 1 and it is not appearing in all, so this T2 will simply become here same as B1, and similarly for all other totals. So, now you can see here, you can finally obtain here the expression for Qj here as say from here Vj minus Tj upon K. So, now you can see here you have obtained the values of the diagonal and off diagonal elements of the C matrix and this Q vector. So, now we simply try to find out here the C matrix also, because ultimately we have to use the generalized inverse of C. So, we are just trying to do our background work, so that we can use these solutions directly in the intra-block analysis of variance. So, now if you try to recall the matrix C was given by R minus n transpose K inverse n. That was in the case of incomplete block design, and R was the diagonal matrix of say here R1, R2, Rv. So, now you are trying to take here all these elements to be here the same R here R, and all other elements are here 0. So, this I can write down here as say R times I. You have to be once again careful here that in the case of incomplete block design, we had used the symbol R to indicate the column vector of R1, R2, Rv. So, now R becomes here say R times I, small r times I. You have to be a little bit careful with my audio, because once I say R is equal to Ri, it does not get clear that whether I am talking of a small r or capital R. So, I will try to be careful, but you also have to be careful. So, what I am trying to say here, that is capital R is going to be a small r into identity matrix, and the same thing will happen with here K. If you remember, you had defined the capital K to be the diagonal matrix of here K1, K2, Kb, and now in the case of BIBD, you are assuming that all K1, K2, Kb they are the same as here K. So, this K can be written here as a diagonal matrix of here K, 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 and this is going to be like here all the elements they are here as K on the diagonal, and all other elements are going to be here 0. So, this I can write down here k times identity matrix, right. And for about n transpose n, we already had found this expression that n transpose n is equal to r minus lambda times I plus lambda into EV1 into EV1 prime or transpose. So, now we have to simply substitute all these expressions here in this C matrix. So, if you try to see, I can write down here C here as Ri, and now this K, capital K inverse can be expressed here as 1 upon K, and then this I will come over somewhat here n transpose I n. So, this will become here n transpose n, and now I try to substitute here the value of n transpose n matrix that we found earlier. Now, we simply have to solve it. So, let me try to simplify it here. This can be obtained here as R into K minus 1 upon K plus lambda upon K into I minus EV1 into EV1 prime. And then in case if you try to use here the relationship that lambda into V minus 1 is equal to R K minus 1. So, I can use here this R into K minus 1 here, and I can write down here lambda into V minus 1, and all other terms they will appear as such. And now, if you try to simplify it here, we will get here lambda V upon K into I minus EV1 into EV1 transpose upon V, this form of here C. Right. Now, we know that C is not a full rank matrix, because we already had proved that the row sum and column sums in C, they are equal to 0. So, the unique inverse of C does not exist, because C is not a full rank matrix. So, now we need to find out here the generalized inverse of C. So, we are indicating it by here this symbol C and here this inverse, but inverse is without 1, because once I try to write down here is like as inverse, this means this is a unique inverse. So, now the generalized inverse of C is obtained as here like this one. C generalized inverse is equal to C plus EV1 into EV1 transpose divided by V and whole inverse, which is here the unique inverse. Right. I am simply using here the concept of Moore-Penrose inverse. Right. So, you need to have a good revision from your linear estimation how this Moore-Penrose is defined. This Moore-Penrose inverse is also a generalized inverse, but the only good quality with this generalized inverse is that this is a unique inverse, because other generalized inverse may not be unique. So, now in case if you try to see here how are we going to find it out, because we have already obtained the C here like this, C is equal to lambda V upon K into IV minus this matrix IV minus EV1 transpose upon V. So, I can write down here, I try to bring this factor here on the left hand side, and I can write down here Kc upon lambda V is equal to the same matrix. Now, we try to obtain the generalized inverse of this quantity K upon lambda V C, and remember K upon lambda V is a scalar quantity. So, now we try to obtain here. So, this K upon lambda V is a scalar quantity. So, that will have a unique inverse, and then the generalized inverse of C, which is going to be here C plus EV1 transpose divided by V and its unique inverse. Now, I try to substitute here the value of here C, what we have just obtained, and then you can see here this term and this term they get cancelled out, and then you have here IV whole inverse, which is equal to here IV, because the inverse of an identity matrix is an identity matrix. So, now I can write down here this quantity here, say K upon lambda V whole inverse into C generalized inverse equal to IV, and hence I can write down here that the generalized inverse of C is given by lambda V upon K into IV. So, an estimate of tau which can be obtained from the reduced normal equation Q equal to C tau in the case of BIBD is given by here tau hat is equal to C generalized inverse into Q, and the generalized inverse of C has been obtained as a lambda V upon K into identity matrix of order V. So, this becomes here lambda V upon K into Q, right. So, now you have obtained here the intra-block estimate of the treatment effect tau. So, you can see here that when we discuss the concepts in incomplete block design, then we had simply mentioned that we are going to find out the generalized inverse of C, because C is going to be a rank deficient matrix. But now in the case of BIBD, because you have a clear cut setup that how the treatments are going to be allocated to the different blocks, you can obtain here the form of this C as well as the generalized inverse of C. Now, once you have obtained here the intra-block estimate of the treatment effect, after that you can conduct the analysis of variance. That will be your intra-block analysis of variance. That means you need to find out the adjusted sum of square due to this tau hat, the unadjusted sum of square due to blocks. From there you have to find out the SSE, because TSS will remain the same, and then you can conduct the intra-block analysis of variance. So, that is what we are going to do in the next lecture. And my request is that whatever we have done up to now, try to do the same algebra with your own hand, own pen, own paper, and yourself. This will give you a lot of confidence, the concepts will get clarified, and at every step ask yourself that why I am doing so, why I need to find the second step, and this will help you in understanding this BIBD, and this will be helpful in the next lecture when we are going to implement it in the intra-block analysis of variance. So, please also have a quick revision of the intra-block analysis of variance. As you have seen that we have simply used here the expression directly from
Swayam Prabha, Digital India, Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture we started a discussion on balance in complete block design. We had learned that how the treatments are going to be assigned in different blocks under the setup of